In active reconstruction, we aim for an agent to autonomously reconstruct a scene. Unlike traditional reconstruction, active reconstruction requires the agent to actively select the next best view. The key challenge is identifying the most informative viewpoint. Existing studies primarily focus on evaluating geometric completeness, exploring unobserved regions, but they lack direct evaluation of visual quality during reconstruction. Recent approaches attempt to quantify visual uncertainty to assess reconstruction quality directly. However, these methods often suffer from low computational efficiency, making them unsuitable for real-time systems. Our goal is to develop a high visual quality active 3D reconstruction system. This requires designing a visual quality metric and selecting the next best view based on this metric while meeting the real-time demands of active 3D reconstruction. This poses the challenge. We need a method to select views based on visual quality both effectively and efficiently. To address this, we first design a probabilistic model to quantify information gained based on image loss from new observations. Using this model, we develop the GauSS-MI metric to evaluate the expected information from novel viewpoints. We begin by defining a probabilistic model for each 3D Gaussian to assess its reliability for rendering. An inverse sensor model updates this probabilistic model based on new observations. Here, CK represents the kth observation, typically an image. The inverse sensor model is designed to correlate with the image loss from the kth observation and the cumulative transmittance of each Gaussian. In this framework, image loss and probability are negatively correlated. Lower loss corresponds to higher probability. In contrast, the transmittance impact on the update rate that a lower transmittance implies a less impact on the model update, as visualized through comparisons of different lines. Next, we construct the GauSS-MI metric for active view selection. The problem setting is that at each decision step, we have a set of candidate viewpoints and need to identify the most informative one. We use Shannon mutual information to quantify the mutual information between the reconstructed map and the observations. We decompose the Shannon mutual information by individual Gaussians and pixels in the image. The resulting formula is reorganized to isolate a term related solely to the measurement probability, which we call the measurement prior. The remaining term, defined as the mutual information reward function, depends only on the inverse sensor model, delta, and the odds ratio of the Gaussian probability. In active reconstruction, since observations are unavailable when selecting the next best view, we define an expected delta by assuming zero image loss for new views. This simplifies the reward function. By substituting this into the main equation, we derive the GauSS-MI metric. Finally, we implement the active reconstruction system using the proposed GauSS-MI metric. The system leverages an online 3D Gaussian splatting reconstruction map, incorporating the Gaussian probabilities. To deploy this on an agent, we design a conventional candidate sampling method, generating viewpoints based on horizontal and vertical linear velocities and angular velocity in yaw. The optimal viewpoint is selected by maximizing the GauSS-MI metric. The chosen viewpoint, along with its motion primitive trajectory, is sent to the robot to execute the movement to the next best view. The robot then captures a new image from this viewpoint, which is fed into the reconstruction module to update the 3D Gaussian splatting map. This iterative process yields a reconstruction model with high visual quality. For the complete methodology and experiments, please refer to our paper. Thank you for watching.